Why do some objects sink or float? In this video, we're going to find out. But first, we need to understand what is buoyant force. Let's start with an example. Let's say that we place an object underwater. The pressure at the bottom of the object will be greater than the pressure on the top of the object because as you go underwater, the pressure increases. And we also know that pressure is equal to force divided by the area. And so force is equal to pressure times the area. This means that the force at the bottom will be greater than the force at the top because force is related to the pressure. We also know that the pressure in a fluid is equal to P naught, the atmospheric pressure, plus rho GH. And so for the force at the top of the object, F1, we can substitute this pressure equation for P1, and we get P naught plus rho GH1 times the area. At the bottom of the object, we have F2, and we can substitute the fluid in a pressure in a fluid equation for P2, and we get P naught plus rho GH2 times the area. Now, the buoyant force is the net force. So it's the difference between F2 and F1. So F2 minus F1 gives us this equation. And notice that P naught A, the atmospheric pressure times the area, cancels out. That leaves us with rho G times H2 minus H1 times the area. Now, H2 minus H1 is basically the height of our object. And let's say that we're looking at a cylinder here. And the volume for a cylinder is the length of the cylinder times the area. So we can substitute V for H2 minus H1 times the area. And that leaves us with the buoyant force is equal to rho Vg. The rho is the density of the water, V is the water displaced, and G is 9.8 newtons per kilogram, which is the gravitational field strength. Now we're going to see how this relates to Archimedes' principle. So we know that Fb is equal to rho Vg or rho Gv, and rho is the density, and density is mass over volume. If we solve for the mass, we get rho v, so we can actually substitute m for rho v, and then we get mg on the right-hand side. So this is telling us that the buoyant force is equal to the weight of the water displaced. And this relates to Archimedes' principle because Archimedes' principle basically states what we see here, which is that the buoyant force on an object equals the weight of the fluid it displaces. So here's an example of what we're talking about. On the left-hand side, we have a container of water. On the right-hand side, we have a block of steel, for example, that we drop into this container. And you'll notice that the water rises up. And so it's displaced. This block has displaced this amount of water. And this amount of water, the weight of this water is going to equal the buoyant force. So that's what we're saying. The amount of water that's displaced is equal to the buoyant force. And you can see that by the area of the water that I've highlighted here. Now we're going to answer the question why some objects sink or float. So when an object is floating, the gravitational force is equal to the buoyant force. And not only that, the density of the object is going to be less than the density of water. If the object's density were greater, then the object would sink. Let's take a look at a situation where it does sink. So this object right here is sinking, the one in the middle. The gravitational force is greater than the buoyant force. By the way, this container is pushing up on this block. Otherwise, this block would be accelerating downward. So I'm not drawing that force. I'm just highlighting the buoyant force at this point. And the object's density is greater than the density of water. So if it sinks, the density of the object is greater than water. If it floats, the density of the object is less than the density of the water. Now, if it's just hanging in the middle of the water, the buoyant force is equal to the gravitational force, and the density of the object equals the density of the water. Now let's take a look at a sample problem. Here we have a block of aluminum, which is fully submerged in water. The mass of the block is 0.5 kilograms. The aluminum has a density of 2,700 kilograms per meter cubed, and the water has a density of 1,000 kilogram per meters cubed. You'll notice that it does sink because it has more density. It has a higher density than water. So we're looking for the buoyant force. Buoyant force is rho vg. Rho is the density of the liquid displaced. And we know that density is mass over volume, so volume is equal to mass over the density. We can substitute the m over rho for the v, so we get rho times m over rho of the aluminum block times g, and we're going to substitute our given values, and we get 1.81 newtons. Now, to calculate the apparent weight of the block, we're going to take the weight of the object, mg, minus the buoyant force. So this is why when you go in water, you might feel a little bit lighter, and that's because there's a buoyant force. It doesn't mean that your weight has changed, but you're not going to feel as heavy because there's another force that's pulling up on you. In this case, it's the water. And so the apparent weight is going to be the weight of the object, mg, minus the buoyant force, and we get 3.09 newtons. Now we're going to take a look at our second problem. We have a wooden block with a density of 600 kilograms per meters cubed, which floats in water. This makes sense because water has a higher density than 600. What fraction of its volume is submerged? We're going to start with the fact that it is floating, so we know that the buoyant force is equal to the gravitational force. And we know that the buoyant force is rho vg. The rho here, just to remind you, is the density of the fluid. The v here is the volume of the object that is submerged, so the volume of the block that is submerged. And then on the right-hand side, mg, we know that rho is mass over volume, so we can substitute rho v for the mass. And this rho on the right-hand side is the density of the object of the block times the volume, the total volume of the block times g. This gives you the weight of the block. And then if we cancel out the g, we can move the rows to the right-hand side, volumes to the left, and we get that the volume of the submerged portion of the block divided by the total volume of the block is equal to the density of the block divided by the density of the fluid. So we substitute 600 over 1,000, we get 0.6, which is 3/5. So 3/5 of the volume is submerged. Now we'll take a look at problem 3. A solid sphere of unknown material is floating in oil. It has a density of 850. The oil has a density of 850. Exactly 75% of the sphere's volume is submerged. Find the density of the sphere. So we're going to use our ratio that we derived in problem 2, the volume of the submerged portion divided by the total volume of the solid sphere is equal to the density of the object, the sphere, divided by the density of the fluid. Since 75% of the sphere's volume is submerged, we're going to substitute that on the left-hand side, 0.75 equals the density of the object divided by 850, which is the density of the oil, and we get the density of the object, 638 kilograms per meters cubed.